Okay, I want to prove a couple basic derivative rules. So the first one is going to deal with continuity. First theorem. If f mapping AB to R is differentiable at x in AB, then f is continuous at x. I want to prove this in two different ways. The first way is going to be our standard epsilon delta proof, and we'll see that that's probably not the best way to go about these things, proving definitions with derivatives. And then the next way, we're going to reference Theorem 4.4 from continuity and from how limits of functions work with addition, multiplication, and division. And we're going to use that theorem to help us shortcut or avoid the epsilon delta proofs that can be a little bit tricky. So the first proof, let's do this with an epsilon delta proof. And this is going to be a little bit messier because we're not going to do the scratch work on the side. We're going to figure out what delta has to be straight from working with some algebra. So proof. Let epsilon be bigger than 0. We need to show that f is continuous, knowing that the derivative exists at x. Okay. Let's make this slightly smaller. So there is a delta 1 bigger than 0 with f of t minus f of x over t minus x minus f prime at x less than epsilon whenever t minus x is less than delta 1. Okay, so delta 1 is going to give us a little bit of a bound on things to start with, and we're going to have to do a minimum delta argument again. And before we do that, what I want to do is I want to use the reverse triangle inequality on this. So using the reverse triangle inequality, we see that absolute value of f of t minus f of x over t minus x minus f prime at x is less than epsilon. Let's add f prime at x to both sides. F of t minus f of x over t minus x in absolute value is less than epsilon plus the absolute value of f prime at x. Okay, what we're trying to bound is f of t minus f of x for continuity in terms of t minus x in absolute value. So now I get to pick my new delta. Let's multiply both sides by t minus x. F of t minus f of x in absolute value. Can make these absolute values a little bit more fitting. It's less than epsilon plus the absolute value of the derivative times the absolute value of t minus x. Okay, so we're going to take delta 2 to equal epsilon divided by epsilon plus the absolute value of f prime at x. Okay, so if we take something smaller than this, then the right hand side would be less than epsilon in this equation. So we're going to take delta equal to the minimum of delta 1 and delta 2. Then, because it's smaller than delta 1, I get to do the algebra I just did. And we get to see that f of t minus f of x is less than epsilon plus f prime of x in absolute value times t minus x. And this is less than or equal to strictly less than epsilon plus the absolute value of f prime at x times epsilon over epsilon plus the absolute value of f prime at x, because delta is less than delta 2 or equal to delta 2, which is equal to epsilon whenever t minus x in absolute value, that's t, is less than delta, which shows f of t goes to f of x, i.e. f is continuous at x. Okay, so that was a little bit messy. There was kind of a lot to follow with some algebra and some epsilon deltas, and it got just a little bit technical. It wasn't too bad, but this was probably the most basic of the derivative theorems we're going to do, and we still had to do some work for these epsilon delta proofs. So let's recall Theorem 4.4 and see an easier way to do this proof, appealing to some theorems about limits that we already have. So recall 4.4. If, okay, I'm going to kind of avoid where things live, but if f of t in the limit as t goes to x equals a, and the limit of g of t as t goes to x equals b, then three things happen. Addition plays nicely, multiplication plays nicely, and division plays nicely, i.e. the limit as t goes to x of f plus g at t equals a plus b. Second thing, limit t goes to x f times g at t equals a times b. And third thing, limit t goes to x f over g at t equals a over b, so long as b is not equal to 0. Right. So we proved those, and there was a little bit of a restriction on what did it mean for t to go to x as a limit point, and some domain and range stuff. But for the most part, we're not going to have to worry about that too much as long as we're dealing with reals. We kind of know what that stuff happens, or how that stuff works in the reals. So let's use this to prove that continuity theorem again. So let me rewrite that continuity theorem. If f from AB to R is differentiable at x then f is continuous at x. So here's our proof using the Theorem 4.4 just to make things a little bit easier. Okay, so we need to show f of t goes to f of x as t goes to x. So we'll show instead that f of t minus f of x goes to 0 as t minus x goes to 0. Okay. So let's look at the limit of f of t minus f of x. Well, that's equal to the limit sort of as t goes to 0, as t goes to x, as t goes to x of f of t minus f of x divided by t minus x times t minus x. Okay, which this goes to f prime and this goes to 0. So by that product version of 4.4, this is equal to f prime at x times 0, which is equal to 0. Okay, so f of t goes to f of x when t goes to x, giving continuity. Okay, so that was a little bit easier. We just had to be a little bit careful of how we applied this theorem of sequences. So I broke it up into two sequences that I knew what they did. It's a product of those two things that I know what they do. Then I can take their the product of their limits and figure out what happens in the limit. We're going to use this similar idea to show that the derivative of the sum of two functions is the sum of the derivatives. We'll show the product rule, and then we'll show the quotient rule. Okay, so theorem. Let f and g from a, b to r be differentiable functions at x. Then three things happen. F plus g, f times g, f divided by g are differentiable at x, with f plus g prime at x, so a equal to f prime at x plus g prime at x, b fg prime at x is equal to f prime at x g of x plus f of x g prime at x. That's my product rule. And c f over g prime at x is equal to f prime at x g of x minus f of x g prime at x divided by g of x squared. That's the quotient rule. Okay. And this is as long as g, not g prime, g of x, as long as the denominator is not equal to 0. That's fine. Okay, so let's prove these, and we're going to appeal to that limit theorem 4.4 to prove most of these. Well, prove all three of these, and that's going to make it a lot easier for us than using epsilon delta proofs for these limits. So, proof. Let's do a first. We need to take the limit as t goes to x of f plus g of t minus f plus g at x divided by t minus x. Okay, we're going to split this up. This is equal to the limit as t goes to x. We're going to do some algebra here and just get f of t minus f of x over t minus x plus g of t minus g of x over t minus x. We'll take the limit of that stuff. Well, by our summation of the limit of two sequences, since each one of these converges by assumption, this is f prime at x plus g prime at x. Checks out for A. That one's not bad at all. B. This one's not so bad either, but we have to do a little bit more algebra in the middle. So the limit as t goes to x of fg at t minus fg at x over t minus x is equal to the limit t goes to x f of t g of t minus f of x g of x divided by t minus x. Okay, so here I can't just use a product thing because I don't know, like, this numerator isn't just the product of derivatives here. So we have to play a little bit of a trick by adding and subtracting something in between so we can factor out the top. So limit as t goes to x. I need to add some stuff. I need to add 0 in a smart way. F of t, g of t. So if I want the derivative of f to start with, what I'd want to subtract is I'd want to subtract f of x from f of t. But there's this g of t here, so we're going to multiply by g of t here as well. That way I can factor out g of t and get f of t minus f of x. Okay, since I subtracted that term that wasn't up here, I'm going to have to add that term back in down here. So this is going to be f of x g of t added back in. And fortunately for me, that means when I add this last term, f of x g of x, I would be able to factor f of x out and end up with g of t minus g of x in the back end. And when we factor those out and divide by t minus x, that's going to make things nice for us. Okay, so let's factor out g of t from the first half. So I get g of t, and then I've got f of t minus f of x divided by t minus x, and then plus, from these guys I'm going to factor out f of x, and what's left is g of t minus g of x over t minus x. So that add and subtract something in the middle allowed us to factor this nicely, and now I can take the limits of each of these parts. So using the product part of 4.4 and the summation part of 4.4, and knowing that g is continuous at x because of the theorem we proved earlier, I see that g of t goes to g of x by continuity of g at x. This goes to f prime at x, just by definition of derivative and being differentiable, plus f of x is just a constant, so the limit of a constant is the constant itself. And this is the derivative of g at x. So that gives me my product rule. Quotient rule is going to be really similar. We're going to do that add and subtract thing in the middle, and we have to do it with a rational function now. So C we're going to take the limit f over g at t minus f over g at x over t minus x as t goes to x. And so let me write this out. T goes to x. I've got f of t over g of t minus f of x over g of x divided by t minus x. Okay, so this is a big sort of rational mess of stuff. I'm going to clear the denominator and the numerator by multiplying both the top and the bottom by g of t, g of x. So I'm going to multiply top by gt gx and the bottom by gt gx. Okay, that's going to give me the limit as t goes to x, multiplying f of t over g of t times g of x gt. That's going to give me f of t g of x, denominator's cleared, minus denominator there clears, but I get f of x g of t, and then I've got t minus x in the denominator here, and I'm just going to multiply by g of t g of x. So now we're going to see where we get those parts. So the left hand side is going to give me the numerator stuff, and then the right hand side here of this multiplication is going to give me the g of x squared in the denominator. So now in the middle here we're going to have to play that same add subtract trick that we played with the product rule. So let's see what numbers I have to put in and what I have to multiply or add and subtract there. So I got f of t and g of x right now. So it'd be nice to have, well, let's go, what do we want to see? In our quotient rule, what we want is f prime to start with, right? F prime to start with, and g of x in that first term. So let's see, what would we have to do to get f prime in this first? I'd have to subtract f of x, g of x, because then the g of x would cancel or factor out, and I'd have f of t minus f of x. So let's subtract off f of x, g of x. And then, because I subtracted it off, I have to add it back in, f of x, g of x, and I need to subtract off f of x, g of t. This is all over t minus x, and it's times 1 over g of t, g of x. I've got equality because I just added and subtracted the same thing in that numerator. Now let's factor out g of x from these first two terms. I can factor out g of x there. So t goes to x. I factor out g of x. I get g of x times f of t minus f of x over t minus x plus, and then in these two I can factor out negative f of x. And if I factor out negative f of x, I put the g of t and g of x in the right order. So I've got g of t minus g of x, which is the order that I want those in, divided by t minus x. That's where that minus sign comes from in the quotient rule. And then multiplied this whole thing by 1 over g of t, g of x. Okay, now that I've got this broken up into the pieces I want, let's make that a bigger parenthesis. We can use 4.4 again, and this gives me g of x big square bracket, f prime at x minus f of x g prime at x, square bracket ends. By continuity, this is 1 over g of x times g of x, or g of x squared. If I put this as a fraction, then I get a g of x f prime at x minus f of x g prime at x divided by g of x squared, which is our quotient rule. Okay, so using these limit rules that we've already proven help us a lot so we can avoid these epsilon delta proofs. It made this theorem much easier, and made that continuity theorem much easier than having to actually kind of dig deep and figure out what delta would have to be given an epsilon.